Hi, this is Mr. Mack. This is the concept video dealing with infinite geometric series. Now, it turns out that some geometric series, when you add an infinite number of the terms together, they ended up being bounded by a number. We say that when the series is bounded by a number, that it converges to that smallest number that bounds it above. Let's see if we can just start out with an example. Maybe this will help some. Imagine, if you will, that we have a square with sides of length 1. Now the area of the square is 1. Now what I'm going to do is I'm going to start out and I'm going to take half of this square. I'm going to take this half right here. Now the area of the part that I've just taken is 1/2. Now the part that I didn't take, I'm going to cut it in half, and I'm going to take half of it as well. Now, this part would be 1/4. Now, and I'm going to add those two together. So far I've taken 3/4 of the area of the square. Now, if I then take the part that I haven't chosen and select half of it, this part would have an area of 1/8. I'm going to add that to that. And then the part that I didn't select, again, I'm going to take half of that. Now this part would have an area of 1/16, and I'm going to add that to that. And then for this part right here, I'm going to take half of what I didn't select, and this would be an area of 1/32. And then I'm going to take half of the part I didn't select, and this would have an area of 1/64. And then if I took the next part, half of the next part as well, this would be 1/128, and so on like that. Now, see, theoretically, I could keep on doing this forever, and I would always have a positive amount, but it would always be bounded by the area of the square itself. So when all of these terms are added up out to infinity, we wouldn't get more than 1. Now, we wouldn't get any less than 1. If you think about it, if you pick any point that's inside the square, not right on the line, but inside someplace, sooner or later, one of these little halves that I'm taking is actually going to take that point. So sooner or later, every point inside the square would be in one of these little rectangles that I'm taking if it wasn't actually a point on the edge. But there wouldn't be any way that this scheme could ever spill out over the square. So we say that this geometric series, because notice, if you multiply 1/2 by 1/2, you get 1/4. If you multiply 1/4 by 1/2, you get 1/8. If you multiply 1/8 by 1/2, you get 1/16, and so on and so forth like that. So it turns out that this is a geometric series. First term 1/2, common ratio is 1/2, and we say that it's bounded by 1. Actually, by the time we get finished here today, we're going to kind of say that the sum of this to infinity is 1. Now, and so what we say is that these kind of series converge to a value. Okay, see, in other words, they squeeze in on a value, they get closer and closer to the value, they don't go anywhere else. Now, if a series doesn't converge to a particular value, we say that it diverges. Okay, now it turns out that the series that converge are the ones where the common ratio, R, is somewhere between -1 and 1. And mathematically, usually what we do is we say, all right, well, we say the absolute value of R is less than 1. And that's another way of saying any value between -1 and 1. Now, let's take a look at what happens mathematically to this sequence as we do that. Now, mathematically, the sum of the first n terms of a geometric series is a sub 1 times 1 minus r raised to the n over 1 minus r. Now, in this particular case, r is going to be equal to 1/2, and a sub 1 is going to be 1/2. And what we're going to do is we're going to pick different values of n. For example, S sub 5, in other words, the sum of the first 5 terms, would be 1/2 times 1 minus 1/2 to the 5th over 1 minus 1/2. Now, notice 1 minus 1/2 is just 1/2, and this is going to cancel with that. So we end up with 1 minus 1/2 to the 5th. Now that's 1 minus 1 over 32, which is 31 over 32. Okay. Now let's try it if we take the first 10 terms. The sum of the first 10 terms is still going to be 1/2 times 1 minus 1/2 to the 10th over 1 minus 1/2 again. Now once again, 1 minus 1/2 is 1/2, and it'll cancel there. So we end up now with 1 minus 1/2 to the 10th. Now that's 1 over 1024, because 2 to the 10th is 1024, which becomes 1023 over 1024. Notice that's just 1024th away from 1. Now let's look at S of sub 20, or the sum of the first 20 terms. That would be 1/2 times 1 minus 1/2 to the 20th over 1 minus 1/2 again. Now 1 minus 1/2 is 1/2, so these go away. And we end up with 1 minus, now 1/2 to the 20th is 1 over 1,048,576. So when we do the subtraction here, we get 1,048,575 over 1,048,576. And so I hope you can see, as the terms are getting larger and as the number of terms is getting larger and larger, our sum is getting closer and closer to 1. Will it ever reach 1? No. It'll almost always be a power of 2 on the bottom and 1 less than that power of 2 on the top. But as these terms get farther and farther, there is no number. See, and this is what mathematicians say. There is no number less than 1 that this ratio won't eventually get closer to 1 then. If you give me a number that's less than 1, but different than 1, no matter how close it is to 1, I can pick a number of terms here and get closer to it than that. So what we say is that there's no number less than 1, but 1 is a bound. So we say the sum of this series converges to 1. Now, if you look at the formula itself, we have S sub n is equal to a sub 1 times 1 minus r to the n over 1 minus r. The only thing that was changing each time as we increased the number was the n here. And if the absolute value of r is less than 1, as you raise, see, that's a fraction. As you raise it to larger and larger powers, this approaches 0. So what we do is we say, effectively, when you have an infinite number of terms, in other words, the sum to infinity is a sub 1 times 1 minus 0 over 1 minus r. And usually we just write that as a over 1 minus r. And this formula right here, although adding numbers to infinity is really much simpler sometimes than the partial sum formula. So we would say the sum to infinity, we usually don't put the infinity here, we just put s is equal to a over 1 minus r, and we can find the value to which these infinite sums converge. Now, let me just say to you, it is extremely important that you make sure that you run this through the test. In other words, this part right here must be true, or that formula is not going to work. In fact, you'll get nonsense, and you need to be careful about that. The only time that infinite geometric series do converge is when the common ratio is between -1 and 1. If it is not, and you use the formula, it's going to give you a number, and that number's just going to be nonsense. So watch out. Make sure that you run the test before you actually use this form. Now, a couple of more things. If you have, let's go back and use this 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus so on and so forth. Now notice this is an infinite geometric series. If you wrote this in sigma notation, it would be written like this. Sigma k equals 1 to infinity of 1 times 1/2 to the k minus 1. Okay, notice that this is the first term when we use k minus 1 for the exponent, because k to the 0, I mean anything to the 0 is 1, and so that would be not multiplying by r, and this is going to be a sub 1, this is going to be r, and that will give you the sigma notation for it. And we put an infinity up here at the top to show that we're just going to keep going forever and ever. But even though we do have infinity up there, we do know the value to which this converges because of the formula, as long as your common ratio is less than greater than -1, less than 1. All right, now let's use the program in the calculator that we just wrote in the other video, which you may not have yet watched, but you might want to pause this one here and go watch the video. I've written the program and we called it summer. And so we're going to use, let's go back and use this one on the square right here, okay? We're going to use this red series right here. When I press enter, it wants the first term, which I'm going to put in as 1/2, and it wants the common ratio, which I'm also going to put in as 1/2. And then when I press enter, it gives me 3 pieces of information. The first line is the how many terms, the second line is the term, and the third line is the sum. So with one term, the term is 1/2 and the sum is 1/2. With 2 terms, the last term is 1/4 and the sum is 3/4. 1/2 plus 1/4 is 3/4. And we can just keep pressing this. Now watch, as we keep pressing this, the terms get closer and closer to 0. Now, at this particular point, it's shifted into scientific notation. That would be 0.0009765625. That's what the E-4 means. And notice the sum is 0.999023. And if you just keep pressing the enter button and watching the terms, notice this sum is converging on 1. It's getting closer and closer to it. In fact, eventually the calculator is going to give up. It's going to say, I really can't distinguish between this number and 1. We've got 28 terms so far. We're getting close here. There's 31, 32 terms, 33 terms. We'd probably get this for a couple of terms, and then at 35 terms it gave up and said, okay, 1. And you can press it as much as you want after that. The sum is just going to stay 1 because you can't get outside that square. So that's a calculator demonstration showing you that there are infinite sums of positive numbers that do converge to a specific value. Now, one of the applications that they're going to run you through is the application of repeating decimals. Now imagine we have the decimal 0.27, 27, 27, 27, 27, 27, 27, 27, with the 2 7s repeating forever. Now, there are a number of ways to find this sum, but one of the ways is to notice that this can be parsed into pieces. This is kind of like 0.27 plus 0.0027 plus 0.000027 plus et cetera, et cetera, et cetera. And if you look at this, the first term, a sub 1, is 0.27, and r would be, for example, 0.0027 over 0.27, If we move the decimal over 4 places here and 4 places here, we get 27 over 2700, which is 1 over 100 or 0.01. So the common ratio would be 0.01. Now, if we use the formula for, oh, by the way, this common ratio is between -1 and 1, so this series is going to converge. And so the sum would be equal to the first term, 0.27, over 1 minus r, which is 0.01. So that gives us 0.27 over 0.99. Now, I can multiply both numerator and denominator of this by 100 to get 27 over 99. And then notice that 9 goes into 27 3 times. 9 goes into 99 11 times, so we get 3/11ths, which is pretty cool. And now watch this. If we take the calculator and we say 3 divide 11, guess what it gives us? 0.27, 27, 27, 27, 27, etc. So you can use this formula to find a ratio of two integers for a repeating decimal. Now, one of the things that happens sometimes is you have a repeating decimal, but the first couple of numbers don't work right. There's an example of that in one of the solution videos. I'm going to refer you to that to take a look at that. Now, that should take care of the things you need to know about infinite geometric series. So we're done.